So, hello everyone. Welcome to the TIFR CAM Colloquium. I would like to introduce Professor Bhat from ISI Bangalore, who will tell us about C-star extreme points of positive operator valued measures. Over to you, Professor Bhat.
Okay, so thank you. Okay, so as I said, I want to talk about positive operator valued measures. So let me begin with some things which I often forget. First thing is the thanks to the organizers. So I don't know who else is there. Nishant, I know, but I don't know who else is there among the organizers.
Ujjwal is here as well. Ujjwal is a organizer along.
Yeah, I'm sorry. I thought I'll make it online instead of coming to TIFR. So because I was just tied up with too many other things. Okay, so this talk is based on this article, which is you can find in the archive. Also, it has already appeared in CMP, okay, Communications in Mathematical Physics, and it's joined with Tathagata Banerjee, who was a postdoc here. Now he's in QSAT, Cochin University of Science and Technology, and my PhD student Manish Kumar. He has gone for postdoc to IIT Chennai, okay, IIT Madras. Okay. So here's the brief of outline. I just want to talk about the C-star extremity of two things. One is POVMs and UCP maps. So my main focus would be POVMs. That these are positive operator valued measures. Okay. And then I will also tell what are these unital completely positive maps, because they are actually very closely connected, the two notions. And so, and then what is this C-star convexity instead of usual convexity, and some results, okay, the main results we have, and some one or two problems. Okay, so that is the scheme. So POVMs means it's short for positive operator valued measures. So it's very useful in physics, many uses. And it's a very simple thing. Actually, it is very much like your usual measures, just that the measures are now, instead of positive real numbers as values, they are taking operators as their values. So here X OX is a measurable space. So X is a set, non-empty set, and you have a sigma field OX. Okay, so this is a sigma field over X, and you have fixed the Hilbert space H. Okay, so then positive operator valued measure. So this means that you have a map, okay, so or the measure mu on the sigma field. So it is taking values in B of H, bounded operators on H, with certain properties. So for every set A, mu of A should be a positive operator. Okay, so these are on the Hilbert space. So positive, you can say positive definite or non-negative definite. So if your H is finite dimensional, so then these are the positive semi-definite matrices. Okay, the positive in the sense of quadratic form. Okay, or you can write A as B star B for some B. So that is what the positivity is. And so for every set A, mu of A should be positive. Instead of saying non-negative, I would always say positive. Okay, and it's a measure in a very weak sense. That is, if you fix two vectors H and K, and you take the entry, the HK entry of mu of A. So if you fix H and K, then it should be a measure, complex measure for every H and K. And if K is equal to H, so then since mu of A is positive, this would be a positive measure. Okay, but if the vectors H and K are different, then you cannot insist that it should be positive, but it would be a complex measure. H equal to K, it would be a positive measure because of this hypothesis, the first one. Okay. So POVM with H equal to C, when the Hilbert space is complex numbers itself, are just the usual positive measures. Okay, so this is a generalization of the concept of positive measures. Instead of positive real numbers, now the measures are taking positive operators as their values. The simplest things which many of you may have seen, the spectral measure. Okay, the spectral measure of a normal operator is a projection valued measure, okay, supported on the spectrum of the operator. Okay, of course, you may enlarge it to hold all subsets of complex numbers if you want, but basically it is supported on the spectrum of the operator. Now, if you take convex combinations of such things, two spectral measures, you would get positive operator valued measures, right? So this way you can construct many positive operator valued measures. So they are also called as generalized measurements in quantum theory. So usual measurements being the spectral measures coming from the normal operators. Okay, so the generalized ones is just abstract any positive operator measures. Okay, so some basic terminology, just like by mu hk, I would always mean this measure defined like this, the complex measure. The POVM is determined by this family of measures mu hk. Right? So once you know these measures mu hk, which are ordinary complex measures, you know the mu. Okay, because you know the coordinates or the entries of the operator mu of a, then you know the mu. Okay. So, and we call the measure as normalized if mu of x equal to identity. So they are like probability measures. Mu of the whole space x is the identity operator on H, then we call it normalized. And you have projection valued measures. If mu of a is a projection for each a, which are of course very special kind of things that when you have projection for every a, and it's a spectral measure, the best situation when it's projection and also it is normalized. Mu of x is identity, and you get only spectral measures as the things to describe through spectral theorem, right? For describe normal. Sometimes you might have this technicality of called regular POVMs. So it just means that when you have X is a topological space and you have the Borel sigma field and these measures mu h comma h are all regular in the usual sense, like approximation by compact sets from inside and open sets, that kind of regularity we might have sometimes. But I will mostly ignore that technicality. Okay. So, and what are these unital completely positive maps or UCP maps? Well, suppose you have two C-star algebras, A and B. So, well, what are C-star algebras? So this bounded operators on a Hilbert space, that is a C-star algebra, but you can also look at their subalgebras, right? Collections of operators which are closed under addition and also product, so that you have an algebra and taking a joint and taking norm limits. These are known as C-star algebras. Okay, so like n cross n matrices, diagonal matrices, okay, such things are C-star algebras. So one special class is the continuous functions on a compact Hausdorff space. So they form a unital C-star algebra where you take the subnorm as the norm. So abstractly, C-star algebras are Banach algebras with some additional conditions, so which I will not go into. So you can just think of C-star algebras as subalgebras of bounded operators on a Hilbert space. Okay. So complete positivity means that you have a map from A to B. So in any C-star algebra, you have the notion of positivity. So you call an element A as positive if you can write it as B star B. Okay. So that is the definition. A is called positive. Then if A equal to B star B, okay, so it corresponds to when you have operators on the Hilbert space, then it corresponds to the same positivity we described before, the quadratic form being positive. Okay, so here the map is said to be completely positive, means it is something more than being positive. So phi is from one C-star algebra to another. So A positive implies phi of A positive. Okay, so this would mean just positivity. Okay. So what we have is something slightly stronger than this. It is the same kind of thing with the matrices with entries from A. So that is a technicality which we will not go into, but it just good enough to remember that it is something stronger than positivity, and in our context, actually just positivity will do in here. The reason for that I'll come into in a minute. And phi is called unital if phi of identity is to identity. Okay. If the domain, the A or B is abelian, okay. Yes.
Yeah, so I just want to clarify. So these maps that you're talking about, they don't respect the product structure. So
No.
C-star algebras don't come. They come with a product structure, right? So they are.
Yes.
So these linear maps. So if they actually preserve the product structure, then they would also preserve positivity in the way that you're describing,
Yes.
right?
So if they preserve the product structure, then we call them star homomorphism. They should put the adjoint and the product structure. Then we call them star homomorphisms. Okay. So if they are homomorphisms, then they will preserve positivity, and they, in fact, they will be completely positive.
I see. So in some sense, this is a weaker version of a star homomorphism. Can I think of it in that way?
Yes, very much, very much. Okay. So you might ask why one looks at that. Like if you have very two simple C-star algebras, like say 2 by 2 matrices and 3 by 3 matrices. So from you will not find any unital star homomorphism from M2 to M3 or M3 to M2. There are none. Okay. Whereas you would like to have maps, and this is a weaker form of that. Okay. And so what are they? So there is a theorem called Stein-Spring's theorem, which I'll mention briefly, which tells you that these CP maps are nothing but you have a star homomorphism, okay, like say pi, then you cut it down by a projection. Okay. So the maps of this kind, A goes to a star homomorphism, but a corner of a star homomorphism. Okay, cut it down by a projection. Such maps, so then it would no longer be multiplicative. Such maps are the CP maps. Okay, so they are cut downs of compressions of star homomorphisms.
I see. Thank you.
Okay. So they are actually sort of basic maps for C-star algebras, because we don't have sufficient number of homomorphisms. Okay. And in this talk, I will be talking only about CP maps from Cx to B of x, Cx being continuous functions, the space of continuous functions on some compact Hausdorff space X, which itself is a unital C-star algebra. So here, just positivity implies complete positivity, because either if the domain or range of a positive map is commutative, then the map is automatically CP. Okay, so that's why here I don't have to talk about complete positivity, it is just positivity. So just positive functions here go to positive operators, that kind of maps. Okay. Okay. So there is a nice correspondence between these POVMs and the UCP maps. So let X be a compact Hausdorff space and let H be a Hilbert space. So actually the correspondence is between regular POVMs and CP maps. Regularity in the sense of regularity of measures. So the idea is very simple. It is like if you have a measure, then you get a linear functional by integrating, right? So that is the Rees representation theorem. And if you have a positive functional, then it comes from a measure. Okay, so that is exactly that. So from a measure mu, the usual measure, positive measure, would correspond to this integral f d mu, which gives you a complex valued function, a positive function, right? Positive functional, right? Mu goes to this integral f d mu, f going to f, so it gives you a linear, positive linear functional. The similar thing, instead of usual measure, if you have operator valued measure, the corresponding thing which you get here are the CP maps. Okay, so that usual correspondence, you know, between positive measures and the linear functionals, right? That is a Rees representation theorem. If you have the positive linear functional, then that comes from a measure. Okay, instead of positive linear functional, if you have a CP map is taking values in B of h, then that comes from a POVM. So that is the connection. So given a POVM, you just integrate the any continuous function f, you integrate. So for every h comma k, you integrate and you get a complex valued, get a linear functional. Okay, so that way, this one f goes to phi mu f, this would define an operator when you vary h and k, and that is the map from Cx to B of h, which is completely positive. Okay. So given any POVM, just by this integral, you get a CP map. Conversely, if you have a CP map, you can look at the coordinates and that the raised Markov representation theorem, or the raised representation theorem. That gives you the measures, and you see that you can put together all the measures and you get a POVM. Okay, so that is a natural correspondence between CP maps and POVMs. Okay, it is just the correspondence what you are familiar with, namely positive measures and the linear functionals. The same correspondence sort of jacked up to CP maps. Okay, so what is this convexity? Okay, there is a new notion here, is the C star convexity. The usual convexity, you know, in any vector space, you can talk about convexity. So same kind of thing, but here there is an additional notion of convexity. So let us see. So we look at the collection of POVMs, normalized POVMs, that we have called as PHX. So that is a convex set, right? Given two POVMs, you can take their convex combination. That would again be a positive operator value measure, just like the way it happens for usual positive measures. But if you look at this convexity and ask for extreme points, it's very difficult to determine. Okay, one can see that the spectral measures are extreme, but no explicit description is available on the set of all extreme points, even when X is a finite set, right? So when X is a finite set, the measures, you know, like if I have a finite set, say S as 1 to n, if you look at the measures on this, so they are just the weights, right? P1, P2, Pn, Pi is greater than or equal to 0, summation Pi equal to 1. So these are the probability vectors. Okay. So this collection, if you take the extreme points are this is again a convex set. The extreme points are the degenerate ones, right? 1 at one place, 0 elsewhere. So you know the extreme points exactly, and all others are actually just convex combinations of this. So it is a very natural thing to look for extreme points because other elements can be described through their convex combinations. But in this, for POVMs, there is no explicit description for the set of extreme points. We know that the spectral measures, that extreme things are when they are projections, they are extreme, okay? But there can be other extreme points. So we have to generalize the notion of convexity. So this is the new notion of convexity. So instead of scalar coefficients, we take operator coefficients. So these TIs belong to B of h, bounded operators on h, with summation Ti star equal to 1. So in the usual convexity, you would have like summation Ti, right? So if I have some alpha I, then you take summation Ti, Ti is non-negative, adding up to 1. So those are the convex combinations of alpha i's. Similar thing here. So it's just that I need to take care of the non-commutativity. So these operators Ti on one side and Ti star on the other side. So this is the convex combination. Okay. So C star convex combination for mu. So C star convex combination of mu i's. Okay. Summation Ti star mu I Ti. So this condition, summation Ti star Ti equal to identity is put to keep the normalization. If you put mu of identity is 1, is what we want. So if mu I identity is identity, so each of this mu I is normalized, then I would like to have summation Ti star Ti equal to identity. So it is just like the condition summation Ti equal to 1 here. Okay. And you put the star on one side just to keep the positivity, right? So if I take a positive operator here, mu I of A would be positive, that would keep the Ti star Ti. If you put that would remain positive. Okay, so that is the reason why we put a star on the other side. So these are called C star convex combinations. So the usual scalar, when you take the usual combination, convex combination, you take numbers between 0 and 1. So they are being replaced by these operators, Ti's. Okay. So we call them C-star coefficients. So if each of these TIs are invertible, then it's called a proper C-star convex combination. Okay, so it's equivalent to having these TIs being non-zero. Okay. So this notion of C-star convexity has been around. So Robert and Paulson introduced it in 1981, and it's gained a lot of importance in recent years. But mostly people are studying C-star convexity for elements of a C-star algebra. So what we are doing here is the C-star convexity for CP maps. So this also has been studied to some extent. So I'll give you some references. So this PHX is a C-star convex set in the sense that if you take measures, positive POVMs, noise, then their C-star convex combination is another POVM. Okay, so here is the definition of C-star extreme point. So in the usual convexity, see if you have a convex set like this. So these the extreme points are these corner points, right? Those things which you cannot write as a convex combination in a non-trivial way. So those are the extreme points. The same thing here. So if I have a POVM mu, if you write it as a proper convex combination, if each of these mu is not equal to mu, but becomes unitarily equivalent to mu, so then you call it an extreme point. So in usual convexity, you would say that if you write an element as a convex combination, as a proper convex combination, all the terms are equal to the original one, then you call it an extreme point. Okay, right? Like this in the square, these extreme corner points, they are only the extreme points, right? Not the points on the edge also, because you can still write them as convex combination in a non-trivial way. So here the non-triviality includes this unitary equivalence. Okay, so that is a one small difference. Okay, so we will see that the spectral measures are C-star extreme, but the main question is, are they all? Okay. So the result we have is that under good situations, C-star extreme POVMs are spectral. Okay. So one has to specify as to what are these good situations. So there are two classes mainly. So good situation one is that for arbitrary x, but H is finite dimensional. Hilbert space is finite dimensional. Then this holds. The extreme C-star extreme POVMs are spectral. Okay, those are things which we know, the spectral measures. And another situation when X is a countable set and H is infinite dimensional. Okay. Finite or infinite dimensional. X is a countable set, then H can be anything. Okay. So two good situations, we know that extreme C-star extreme points are spectral. So this is in contrast with the usual extreme points. As I said, for usual extreme points, even when X is a finite set, we don't know as to what are all the extreme points. So we just know that the spectral POVMs are extreme, but we don't know the full, we don't have a full description. Okay, we sometimes get some characterizations, but no full description as to what are. But if you, instead of talking about extreme points, if you talk about C-star extreme points, so in a way, a stronger kind of extreme points, then only POVMs, only the spectral ones are C-star extreme points. Okay, so in the context of CP maps, it means that only C-star extreme maps are the homomorphisms. Okay, not the others. So, but once again, this is true only for C-star extreme things under good situations. Usual extreme points, even under good situations, you have other extreme points. Okay, and there are non-spectral C-star extreme points when the space X doesn't fall under such things, like even as simple as X is an interval or a circle with H infinite dimensional, there are other extreme points. Okay, and we don't know that the general situation is still unclear. Okay. Okay, so there are two basic tools needed here. So one is the Naimark's dilation theorem, which says all POVMs, okay, come from the spectral things through a compression. Okay, so if you take a positive operator valued measure, okay, so mu of A you are taking. So in a way you can enlarge it. Okay, you can take a bigger Hilbert space and add other entries, and you make a bigger operator pi a. Okay, so you can have it such a way that this pi a is actually a spectral measure. Okay, so any POVM normalized, I think you will, well, otherwise the picture would look slightly different, that's all. So any POVM, sort of, you can enlarge it, sort of spectral measures. Okay, so this is called Naimark's dilation theorem. All POVMs come from spectral measures to compression. So this is, well, there is something called minimality there, sort of a minimal way you can do it, and then it is unique. But that's not so important for us. But, and this dilation, this is called a dilation, it's called a Naimark dilation of mu. So the comment you can ignore. So this is the POVM analog of time-springs representation theorem, which I mentioned just a few minutes back, namely that CP maps. So you can dilate them, you can enlarge them to get star homomorphisms. CP maps are compressions of star homomorphisms. So similar analog of that for POVMs is this. Okay, you can enlarge the POVM, make it larger, you make the Hilbert space larger to have projections. Okay, so that can be done. Okay, and another basic tool is the Radon Nikodym type theorem. Okay, again, for measures, you are familiar with the Radon Nikodym type theorem. When one measure is dominated by another, you have the Radon Nikodym derivative. Here there is something similar. So you take a POVM mu, you take another POVM mu which is dominated in the sense that mu minus mu is also a POVM. So this is a domination in a stronger sense. In the usual way, all I need is that mu of some set A is 0 implies mu A equal to 0. So that is the absolute continuity. Mu of A equal to 0 implies mu A equal to 0. So that is the absolute continuity which you need usually, right? And then you have a Radon Nikodym derivative. So this here we have a stronger restriction. Mu is actually less than or equal to mu. So that is for every A, mu of A is greater than or equal to mu of A. Okay. So if you have that kind of stronger restriction, then you can get this mu from from mu through some kind of compression. So this is represented now using the previous theorem. That is, you have the for this mu, you have the Naimark dilation. So there you have a spectral measure. So from that you compress. So this is this D corresponds to the Radon Nikodym derivative. Okay. So anything dominated by mu can be got by multiplying by something in the commutant. Okay. So which behaves like the Radon Nikodym derivative. Okay. So this is represented using the previous theorem, this theorem, Naimark's dilation. So it is this pi. Okay. So we said any mu can be got from a spectral measure. So you multiply that spectral measure with a positive operator D. Okay. And so it's written as a positive contraction. You multiply that and then compress. That way you can get all the things dominated by mu. Okay. So there is a similar theorem for CP maps proved by ours. Okay, I don't really didn't put a reference for this because I think it's very well known, and I can't really find out who put it first. Okay. Okay, so whether a given POVM is extreme or not, though it is difficult to describe all extreme points, there are some criteria, the abstract characterizations in terms of this Naimark dilation. So one such is here, so which says that mu is extreme if and only if a map here, okay, using the dilation D goes to V star dV, so that is injective. Okay, so again there is a similar theorem for CP maps which I will not go to, but what this means in particular that every spectral measure is extreme. Because if you have a spectral measure, then there is no need to dilate. This map will be just the identity map. So it is naturally injective. So that's why we get the spectral measures are extreme. Okay. Now, the similar theorem for C star extremity. Okay, because we generalize this concept of extreme things to C star extreme. So this similar theorem was proved by Ferenczi and Zhou. That is somewhat technical. So again, it is in terms of this Radon Nikodym derivative, but a somewhat technical condition, which I will not go into. Instead, there is a corollary to that, and so this corollary to Zhou, which tells you when a mu is C star extreme. Okay, so this description is somewhat simpler. So which says that anything, if mu is C star extreme and anything is dominated by that, then that is in a sense comes directly from mu. Okay, so this I can give you a comparison. Okay, so look at this case. Okay, so here, see that we are now talking about the usual measures. Okay, so that our convex set consists of this kind of tuples, probability vectors. So the extreme points are these, the degenerate ones, 0, 0, and 1 somewhere, everywhere is 0. Okay, degenerate measures. So how do you detect a given Q is extreme? You see the things which are between 0 and Q. Okay, so 0, so this P is need not add up to 1, but PIs are non-negative. Okay, so the things dominated by Q. So you see, if it is extreme, anything dominated by Q is a multiple of Q. See, so because the extreme ones have this kind of thing, 0, 0, 1 somewhere, everything else 0. So if I have something dominated by this, it will be of this kind, some Qj 0, 0. So anything dominated by this is a multiple of this. Okay, so it's exactly same kind of thing. So you identify whether something is extreme or not using the Radon Nikodym derivative. So you see the things, whether it is, what are the things dominated by Q. So they should be coming from Q. They should be in some way multiple of Q. Okay, so that is the criteria we are having here. So you take a POVM mu, okay, normalized POVM mu. So when is it extreme? Look at all the maps which are dominated by that. If they come from directly from mu, just by scaling, okay, mu of A, some T star T, okay, so it corresponds to scaling. So all the things dominated by mu come from mu by scaling, then mu is C star extreme, okay. So this is useful criteria and we use that, okay. So the crucial step we have, so what is our goal? We want to, our goal is here, I mentioned it here. Namely, that we want to say that under good situation, the C star extreme POVMs are spectral. Okay, so like in this kind of case, for arbitrary case, but H finite dimensional or X is countable. In such cases, we want to show that the C star extreme points are all spectral. So that means I want to show that mu is C star extreme, then mu of A is a projection for every A. Okay, whenever is C star extreme, mu of A is a projection for every A. So that is what we want to show. Okay, so the crucial step there to show that is this. Okay, so let mu be a C star extreme point. So suppose I have E which commutes with everything dominated by that. So that is okay. So just have a look at it. So you take any A subset of E, then mu of E commutes with mu of E. Okay, it is very similar to the kind of things we had. You see, when I have 0, 0, 1, 0, 0, 0, anything dominated by that, it's a sort of determined by this. The same kind of thing we are having here. So, but now this is at one point. Okay, you fix one E. At E, it is such that anything for every A subset of E, mu of A commutes with mu of E. Okay, then mu of E is a projection. Okay, so this is also here, you see a projection 0, 0, 1, 0, 0. That's a projection. So how do we prove this? So this is a sort of main tool. with this, we are able to prove that main theorems, the main results what said. So, instead of a condition on the Radon Nikodym derivative, here you have a condition that condition of commutativity. Okay, so this is the condition for any A contained in E, mu of E commutes with mu of, then mu of E is automatically a projection. Okay, so this happens whenever mu is a C-star extreme point. So we are trying to identify C-star extreme points. So one property it must have is this. Okay, so whenever E is something special, okay, any mu of A commutes with mu of E with a subset of, then mu of E is a projection. So how do we show that mu of E is a projection? So, well, what are the projections? Projections are operators, say operators A, which satisfy, they are self-adjoint, and they are also A equal to A square. The square is itself. A equal to A star equal to A square, then that is a projection. So among normal operators, the self-adjoint operators A, which satisfy A equal to A square. So these are all projections. So you can also describe them as in the spectrum, normal operators with the spectrum contained in just 0 and 1. Okay, are the projections. See, A equal to A star, so they should be self-adjoint, means the spectrum should be real. Then element lambda should be equal to lambda square. That means the elements, the spectral elements have to be either 0 or 1. Okay, so what we want to show is that this mu of E is a projection. So what we show is that the spectrum of mu of E intersected with the interval R to S is empty. So you look at the interval 0 to 1. Okay, now any of this mu of E, so this is a normalized POVM. Okay, so all this mu of E are all positive, and they will be less than or equal to identity, because mu of E plus mu of E perp is identity, right? Just like the usual measures, they would be between 0 and identity. Okay, so that means usual probability measures. So mu of E would always be between 0 and identity. So mu of E would have spectrum in the interval 0 to 1. Okay, so what we are trying to show is that you take any R and S, the spectrum is outside of this R and S. So if I show that for every R and S, okay, between 0 and 1, that will show that the spectrum consists of only 0 or 1, right? Because as soon as you intersect the spectrum of mu of E with this interval, any open interval like this, it is empty. So that is what I'm trying to show. And how do we show that? So we use the Zeus criteria, this criteria, namely you look at the things dominated by this and look at the Radon Nikodym derivative. So to see the things dominated by this, so we construct this, so given this R and S, the fixed R and S between 0 and 1, we look at this function, define this function from 0, 1 to 0, 1. So I can explain that function better here. So what is that function? So this function 0 and 1. So we have fixed some R and S. Okay. So this function is just 1 here outside R and S. Here also it is 1. So here it is something like this. Okay, something which is continuous here, but goes down and stops here. Okay, so there is a jump at S, but otherwise it's a nice continuous function. Okay, so definitely it's a measurable function. Okay, so this function, so outside R and S it is 1. So in between, I've defined it some way. It doesn't matter exactly how it looks. Well, it matters because it has been chosen very carefully so that it has certain properties which you will see later. Okay, but now what you see is that it is between 0 and 1, and it is strictly positive. Look at this function; it will be strictly positive and between 0 and 1. So we use the functional calculus or spectral calculus, and you can define f of an operator. Okay, so this is a Borel measurable function, so you can use the measurable functional calculus. and we can define f of t for any t. So our t will be between 0 and identity. So f of t also will be between 0 and identity. And since this function is strictly positive, okay, means it keeps a distance from 0, it will ensure that f of t is invertible. Okay. So what I need to do, I need to, given this measure mu, I have to come up with a new measure which is dominated by mu, and then we apply the Radon Nikodym theorem. Okay, Zoo's criteria for the Radon Nikodym theorem. Okay, so the new measure is defined like this. So you modify the original one, mu, using this function f. Okay, but within E. Outside E, you don't change. So you have a subset E. So you just change there. Okay, like this. Okay. Well, the function is chosen so that this mu is and this measure is defined. So that's again a POVM and is dominated by mu. So you can apply those criteria. So, and mu is C star extreme. So that means nu b has to be given by some operator like this. Okay. So that is the way we use the tool, the characterization. So then you look at the polar decomposition of T. So just like usual complex numbers have polar decomposition, for operators also have polar decomposition. And usual complex numbers, the polar decomposition is unique whenever it is non-zero. The same thing here, whenever it is invertible, the polar decomposition is unique. So you use that, and what you get is that you get a modification of mu of E. Okay, you get this function. So you get this from the polar decomposition. You get a unitary U, and you get a function of S. S is just mu of E. You get a function of S and S unitarily equivalent. Okay, so this is the thing. Okay, a function of S, again using functional calculus, you get a function of S and S are unitarily equivalent. So this is a function which comes from the F by just this computation, and this function, you see, is T between R and S, and R when it is in between R and S, which is a function like this. Okay, R, S. So it is T here, then a constant R, and then jumps to again like this. The main point is that the range of this is outside the interval R to S. Okay, so that is what. That is the crucial thing. The range of this G is outside this R to S. Okay, so it takes the value R, but it does not take any value in between R and S. Okay, so sorry. So S and this function of S are unitarily equivalent. So that means their spectrum should be same. So the range of G does not contain any point in between R and S. And when you have function, the spectrum is the range. Okay, so that means the spectrum of S is contained here, and that is what we wanted to show. It does not contain any point in between R and S. Okay, so that is empty, and that proves the theorem. Okay, so that gives mu of E is a projection. Okay, now so that is the main tool. So using that, we can get several results. So one, like so this requires that you have a set E, so that anything within that is commutes. So a typical case that happens is when you have atomic things. Like what are atomic things? Okay, so you call A as an atom for mu when mu of A is not 0, and whenever B is contained in A, either mu of B is 0 or mu of B equal to mu of A. So then you call A as an atom. So you see, whenever A is an atom, this anything contained in A, this mu B will commute with mu of A, because either it is 0 or it is whole of mu of A. Okay, so whenever you have an atom, you can apply the previous theorem because you get the commutativity for free, because it is either 0 or mu of A. So, and you call measure mu is atomic. Is a definition for every A in A, there is a with mu of A not 0, it contains an atom. Then you call it atomic and call it non-atomic otherwise, if it has no atom. Okay. So every, not otherwise, when it has no atom. Okay, they are two different things. So one can show that every POVM decomposes uniquely as sum of an atomic and a non-atomic. And if you take a normalized POVM on a measurable space X, so this theorem now follows. Because if you have an atomic POVM, so everywhere you can apply that theorem, the previous theorem, so you get commutativity for free, and that will give you that that mu of A is a projection for every A. Okay, because the conclusion was that mu of E is projection, right? So you get mu to be spectral. So in particular, if X is a countable measure space, then any C star extreme point is spectral, because in the countable case, all the measures would be atomic, so it is automatic. So all the results follow for finite sets, countable sets, everything follows because the result has been proved for the atomic case. Okay. And any C star extreme point you can decompose in as an atomic one and non-atomic one. In the atomic case, we know exactly what are the extreme points, C star extreme points, which are, they're all spectral. Okay. In the non-atomic case, we don't. Okay. How it works, we don't. So that is one case, the atomic case where we apply the theorem. The another case, you sort of explicitly assume that the range is commutative. If your POVM is such that mu of A and mu of B commute for every A and B. So everywhere there is commutativity, so you can apply the theorem, and so it follows that you get a spectral measure. Okay. So this is, we have proved for C star extreme things. Earlier, similar result was proved for extreme, the usual extreme points also. If you have commutativity, then you get spectral. Okay. So another situation where you can apply the things is when H is finite dimensional. So there again, you get some sort of atomicity for free. So that is why when the range is finite dimensional, then things follow quite easily. Okay, so H is fine. It is when it is continuous, and you have the continuity. The spectrum can have things which are not eigenvalues. Those are the ones which create POVMs. Okay, here in the finite dimensional case, it's easier. Okay. So again, we show. So this here, the proof is somewhat indirect. Whereas the commutative case, this one was sort of straightforward, just follows directly from the main result. But here we had to work a bit and somewhat indirect. So we first show that it is atomic and then show. Okay. Now, whatever we have done for POVMs, that can be applied to the CP maps, and the same kind of notion, the C star extremity notion we have for C star for CP maps, it's exactly the same. Okay, summation Ti star Phi Ti that you call as C star convexity. Okay, and the criteria here for C star convexity was already proved by Ferencz and Morens, and it is well, this definition due to Ferencz and Morens, and you can sort of translate from whatever was result we have for POVM, you can translate it to UCP maps, the Unital Completely Positive maps. So here is the main theorem. A normalized regular POVM mu is C star extreme in the set of regular POVMs if and only if the corresponding UCP maps is C star extreme. So this gives you a way of moving from one to another. Okay, so what is C star extreme in the case of POVM would give you C star extreme in the case of UCP maps. Okay, you can go back and forth. So immediately we get results for UCP maps, which now the spectral things there, the spectral measures which we had there, translate to star homomorphisms. Okay, so that is the kind of thing. So here, for instance, there we had sets supported on finite sets or countable sets. So the similar thing we here, you have a commutative unital sister algebra with countable spectrum. Okay, so that corresponds to that Cx with x countable or finite. So even in the case when x was finite, the criteria was not clear whether all the sister extreme points were not clear. So, but we now know that there are spectral in the sense of POVMs, but if you come to CP maps, that means they are star homomorphisms. Okay, so we can apply this to a special sister algebra generated by a single normal operator with countable spectrum. So this is the thing, the countable spectrum. Okay, it's a countable set. The spectrum is countable set. So then we are able to apply, because this is again, you see the countable spectrum. So we are not able to apply it to normal operators like multiplication by x on the interval 0 to 1, because you don't have countable spectrum. But in this case, so when you have this kind of nice things like the finite or countable set, then you can see the sister extreme things. Okay, so here is a special, is basically an example of where one can one knows sister extreme points precisely. Okay, and it comes from reducing subspaces. Okay, so I will not go into the details. It's just an example. And similar example, when you have uncountable many points in the spectrum, comes from Hardy space, and there we know that you like a natural CP map. Okay, multiplication by f compressed by a projection, a very natural CP map. So, and that is it gives you a sister extreme point which is not a star homomorphism. Okay, so in general there are extreme points, even sister extreme points, which are not star homomorphisms. Okay, but with uncountable spectrum, with whatever we did, we are in fact we are able to show that in a very general situations there is always a sister extreme point which is not a star homomorphism. Okay, so this is a sort of result going in the negative direction. So you sort of classify the simple ones, and this is a sort of in the other extreme case there are always extreme points which are not star homomorphisms, but there are still some cases where we don't know, okay, as to what is happening. So one such case is this. So our sister extreme unital on the sister algebra L infinity always star homomorphisms. This is this does not fall under any of the cases we covered because the spectrum is not countable. Okay, it is uncountable, and here we showed that there is always something which is not a star homomorphism, but it involved a condition here as a separability. Okay, it is a separable commutative, so that separability is violated. So this case we are unable to show. It looks simple. So in other words, small L infinity. So what are the sister extreme points? We don't know. Okay. So that is open, and of course the general case is open, but if we know this, it might give us some idea as to how to go about for the other things. Okay, so I think I have a few minutes, but I think it's better to stop so well, the spectrum here is a Stonesic compactification, very standard things, but it's not materializable and we don't know how to handle it. Okay, but let me stop with that.
Let us thank Professor Bhat for this wonderful talk. And I open the floor for questions. Please unmute yourself. Feel free to unmute yourself and ask questions if you like. So I have one question, maybe somewhat silly one perhaps. So what I understand from the talk is that we are looking at this notion of convexity that you have, and we are trying to understand extreme points. And I think Is there much understood about the topological structure of the simplex? So here you're of course trying to find out how these extreme points are actually related to your to the object that you're in question. But for instance, a question which often turns up in algorithmic theory is, what kind of a simplex of probability measures do you have? Are the extreme points dense in your topological space? Are these questions at all of interest, or they are completely tangential?
No, they are definitely of interest. The key thing is that all good situations, when we are able to show that the extreme points are star homomorphisms, then things are better. Okay, or when we show that they are spectral measures, then things are better. We know roughly how it looks. Okay, but other case it is completely vague. We have no idea as to how this extreme points look like when you are unable to get a handle on the extreme points. So when they are not star homomorphisms, we have characterizations. If this happens, then it's an extreme point. But how to construct them, we don't know. Okay.
For instance, is there a hope that these are Poisson simplexes or something of this sort, that the extreme points are dense within the entire space?
Yeah, they are not dense. But there is something called Crane-Millman theorem.
Yes.
Which says that all other things can be constructed out of these extreme points. Okay, right. That holds. Okay, so you can construct all the POVMs using these C star extreme points, using these convex combinations and taking their limits.
I see.
Okay, so that is a Crane-Millman theorem. Right. Which we are able to.
Right. So Crane-Millman applies in a very general setting.
Yes. Yeah. So the thing is that it's not enough to take the convex combinations, but one has to take some limits in suitable topology. But with that, it is possible. But the thing is that you cannot apply it much, because if you don't know what are the extreme points.
Sure.
Okay. So most cases here, we don't know what are the extreme points. Only very good situations, simple situations like the finite set, countable set, things like that, we know what are the extreme points.
Is there some sort of conjecture or some like idea what a general situation might look like? Or
I don't think there is any structure, expected structure, no. Because more and more cases, one can try to show that it is star homomorphisms. But then there are situations where we know that they are not star homomorphisms. So like this L infinity case, if one understands, maybe it can give you some idea.
Okay, that's very interesting. Yeah. Are there other questions from the audience? If not, let's thank the speaker again for this wonderful talk.
Okay, thank you.